Oftentimes there's a chemical reaction that happens slower than we want it to, or it requires too much heat, requires too high of a temperature to be done efficiently or safely or cheaply. And in those cases, we can use a catalyst. A catalyst can allow us to reduce the activation energy that's required for a reaction to happen. Remember, when a chemical reaction is happening, we're relying on the chemicals bouncing around, running into each other in the correct orientation to have an effective collision. If you were in my class, I would send somebody up to the front and I would give them a really simple task. You have to put these mega blocks together. It's kind of like an addition reaction, right? We have reactant A, we have reactant B, they come together and they make a product. But you have to simulate a chemical reaction. And so that means you're not allowed to line the mega blocks up and put them together like this. You have to take one of them, throw it up in the air, and whip the other one at it. And you can do that over and over and over and over again. And one time, one kid actually got them to stick together. But you quickly see that if you're just relying on them to come together in the exact right orientation with sufficient speed, it's going to take a lot of collisions in order for them to do that. So in your chemical system, right, these reactants are going to have to collide a lot of times ineffectively before they can collide once effectively. So what does a catalyst do? A catalyst increases the number of effective collisions that are going to happen. And there are a number of different ways that catalysts can work. But often what they do is they help reactants to line up in the correct orientation. So for my reaction here between the carbon monoxide and the nitrogen dioxide, we had to transfer one of these oxygens from the nitrogen over to the carbon. So that means that if they collide like this, right, with the oxygens overlapping, it's not going to be an effective collision because the oxygen needs to interact with the carbon. Metal catalysts are fairly common types. You find them in catalytic converters in cars. And what metal catalysts will do is they'll hold one of the reactants steady in the correct orientation. So for this one, I need the carbon to be accessible by the nitrogen over here. So for this catalyst, if the catalyst can grab on to these carbon monoxides and hold them like this, so that the carbons are facing out, then as this second reactant comes in, it will sometimes collide ineffectively, right, if the nitrogen and the carbon run into each other. But there'll be a much greater chance that as this guy runs into it, it will collide effectively. And so we'll have a much higher reaction rate. In the mega blocks example, that would be like if we taped one of them to the wall and you just have to throw one of them at the one that's taped, right? You don't have to throw them both together. You would have a higher success rate. Biological catalysts, which if you've taken biology, you'll know them by their name, enzymes, they are even more effective than metal catalysts because what they do is they have an active site and they have another active site often. And so they'll grab onto this reactant and they'll grab onto this reactant. My hands are like the catalyst, right? Grab onto the two reactants. As they grab onto them, they'll change shape and they'll bring them together in just the correct orientation. So really, when I give these to my 4-year-old or my 2-year-old and I say, put the mega blocks together, they are acting like an enzyme because they grab the one with their one active site, they grab the other one with their other active site, and they bring them together in just the correct orientation. And when you do it that way, you can do it with a lot less speed, a lot less kinetic energy, so you need a lot less heat in order to make it happen. Now, in my potential energy diagram, what that means is that I don't need to go all the way over this activation energy hump if I have a catalyst, because the catalyst is going to increase effective collision. It's going to reduce the amount of energy that's required. We often show catalyzed reactions with a dotted line like this. So my dotted line would be the catalyzed reaction, and my solid line is the uncatalyzed. Now you'll notice that the activation energy is different. So with my catalyzed reaction, the activation energy was the difference between here and here. For my catalyzed reaction, it's less. For the catalyzed reaction, the activation energy is smaller. It's the difference between these two parts of my graph. But did the enthalpy change? The enthalpy of the reaction would be this line here. difference between the potential energy of my reactants and the potential energy of my products. Does that change? Well, no, because the enthalpy of the reaction doesn't include the activation energy. So whether we have a catalyzed or an uncatalyzed reaction, the enthalpy of the reaction will not be affected. The enthalpy of the reaction does not change.